Hello, and welcome to Differential Equations. This is lecture 19, Electric Circuits. Last time, we talked about mass spring equations. With damping. This time, we're going to talk about the same equations, but in a different context. They're going to show up when modeling RLC circuits. Okay, so we're going to consider a simple electric circuit. Right, so the cartoon for this is that we're going to have something like this. Okay, and so I'm going to put a V over here for voltage, I for the current, R for resistance. L for the inductance. Then capacitor with a charge Q. Okay, and while we're going over this, we're going to have an analogy with water flowing in a pipe. Okay, so let's go over these elements one at a time. First, the circle is a source of electromotive force, right, which gets abbreviated as EMF, or voltage, V. So for example, think of a battery. Which drives the electric charge and produces a current, I. Right, so I is analogous to the rate of flow of water in a pipe. V is like a pump. Producing pressure, right? That's what the voltage is supposed to be like. That causes the water to flow. Right? So incidentally, voltage, right, or volt in general, is named after Alessandro Volta, an Italian scientist who lived from 1745 to 1827, who produced the first electric battery and thereby proved that electricity could be produced chemically. Before that, it was thought that electricity was something that just had to do with living beings. He was admired by Napoleon, who made him a count. Right, the next element is this sawtooth sort of thing. So this is a resistor. Of resistance R, which opposes the current by producing a drop in EMF of magnitude V sub R, which is equal to R times I, with R some constant. Right? This equation is known as Ohm's law. Okay, so this is analogous to friction in the pipe, which opposes the flow by producing a drop in pressure. Okay, so Ohm's law is named after Georg Simon Ohm, a German physicist who lived from 1787 to 1854, whose only significant contribution to science was the discovery of Ohm's law. And the reason for that is that when he announced it in 1827, it was considered too good to be true and was not believed. Ohm himself was considered unreliable and ended up resigning his position at the University of Cologne. His work was eventually recognized, and he was awarded the Copley Medal. This is the most prestigious award of the Royal Society in London in 1841. Right? Okay, so the next element, this curly bit, this is an inductor. Of inductance L, which opposes any change in the current. By producing a drop in EMF of magnitude V sub L, which is L times the derivative of I with respect to t. Right, so this is analogous to a kind of inertia in the pipe that opposes any change in the flow by producing a drop in pressure if the flow is increasing and an increase in pressure if the flow is decreasing. right? And then the final element is a capacitor, right? Or condenser. Of capacitance C, which stores the charge Q. The charge accumulated by the capacitor resists the inflow of additional charge. And the drop in EMF arising in this way is V sub C 1 over C times Q. Furthermore, since the current is the rate of flow of the charge, and hence the rate at which charge builds up on the capacitor, we have the capital I is equal to the derivative of Q with respect to T. Okay, so this is, think of the capacitor as being like a cylindrical storage tank. That the water enters through a hole in the bottom. So the deeper the water is in the tank, which you should think of as Q, then the harder and pump more water in. And the larger the base of the tank is, right, which you should think of as C, for a given quantity, the shallower the water in the tank, and the easier to pump more water in. Okay, the unit of capacitance is measured in farads, which is named after Michael Faraday, a British scientist who lived from 1791 to 1867. Faraday grew up poor and was largely self-taught. He was apprenticed to a bookbinder. but he became one of the most influential scientists in history for his contributions to electromagnetism and electrochemistry. Okay, so those are the different elements of the circuit. These circuit elements follow Kirchhoff's law, which states that the algebraic sum of the electromotive forces around a closed circuit is zero. Okay, so here Kirchhoff refers to Gustav Kirchhoff, a German scientist who lived between 1824 and 1887. He's also famous for his work in spectroscopy. Right? Spectroscopy is the determination of chemical compositions of elements or molecules by analyzing the frequencies of emitted light. So what Kirchhoff's law looks like for us is that V minus V sub R minus V sub L minus V sub C is equal to 0, right? Or if we plug in the equations we've written for each of the elements, that's V minus R times I minus L times the derivative of I with respect to T minus 1 over C times Q is equal to 0. Or we could rewrite that as L times the derivative of I with respect to T plus R times I plus 1 over C times Q is equal to V. Now, depending on the circumstance, we may want to regard I or Q as the dependent variable. Right? In the first case, right? So if we want to think of I as being the dependent variable and this as being an equation for I, then we eliminate Q by differentiating both sides of the equation with respect to T. And replacing dq dt by I, right? So that turns this equation into L times the second derivative of I with respect to T plus R times the first derivative of I with respect to T plus 1 over C times I. And on the right-hand side, we end up with the derivative of V with respect to T. In the second case, right, so the second case, we want to think of Q as the dependent variable. We want to think of this equation as being an equation for Q. Then we simply replace I by dq dt. And so the equation becomes L times second derivative of Q with respect to T plus R times the first derivative of Q with respect to T plus 1 over C times Q equals V. Right, so in either case, whether you want to think of this as being an equation for Q or an equation for I, you end up with a second order linear ordinary differential equation with constant coefficients, right? And forcing term given either divides the voltage or the rate of change of the voltage with respect to time. Right? Note the similarity with the damped mass spring. Equation with the correspondences where before we had mass, right, given by M, here we have inductance given by L. Before we had viscosity, gamma, and now we have resistance, R. Before we had the stiffness of the spring, K. And now we have the reciprocal of capacitance. And whereas before we had displacement, X, now we have charge, Q, on the capacitor. Right now, often the voltage is not constant, right? So our forcing term is often not constant, but instead varies with time. For example, the voltage from a wall outlet in your home is given by a sine curve. Okay, but now that we know that there's a correspondence between the mass spring equations that we studied in the last couple of classes and this equation for the charge, we can use this analogy to import some of the observations we've made. So the analogy between mechanical and electrical systems allows us to import conclusions from there to here. So for example, sticking with the case where the forcing function is periodic, we know that the given electric circuit will have a critical resistance below which the free behavior of this circuit will be vibratory with a certain natural frequency. A forced steady state vibration of the charge Q and resonance phenomena that appear when the circumstances are favorable. Right, so we don't have to repeat our analysis of this sort of equation. We can just recall that we've already studied this equation when we were working with mechanical systems, and then just import what we've learned to these electrical circuits. Okay, so instead of repeating, let's think about the use of complex numbers and how that might make it easier to work with this sort of equation. So this is a good moment to point out the following trick. Very common in electrical engineering, of using complex numbers to handle equations like, let's write down the one for the current. So L I double prime plus R I prime plus 1 over C I equals. So if we were to think of our voltage as being, say, V naught times cosine of omega t, then the right-hand side of the equation for the current has the derivative of the voltage with respect to time. So here I would end up with minus omega times V naught times sine of omega t. So suppose you have an equation like this. So here's what we do. We stare at the right-hand side, and we want to use complex numbers to avoid working with trigonometric functions, instead just work with exponential functions, right? So here's what we'll do. We'll notice that sine of omega t is the imaginary part of e to the I omega t, right? If we prefer to work with real parts, that's the real part of minus I times e to the I omega t. And that allows us to rewrite the equation as L times I double prime plus R I prime. So 1 over C I is equal to the real part minus I e to the I omega t. Actually, no, I left out the coefficient. So since I already had here a minus omega V naught, here I should put I omega V naught e to the I omega t. Okay, And so instead of just having the right-hand side involve complex numbers, now we're just going to allow everything to involve complex numbers. So instead, we want to solve the equation L times I tilde double prime plus R times I tilde prime plus 1 over C I tilde equals I omega V naught e to the I omega t, with I tilde a complex number valued function. Right? With the idea of taking the real part of I tilde to find I, right? So the idea is we're going to solve this equation where now we're working firmly within the complex numbers. And then once we've solved this equation, you take the real part of the solution and you've found a solution to this equation. Okay, so you might think we've just made things worse. We've gone from a second order equation to a second order equation, but now we have to work with complex numbers instead of real numbers, right? The advantage is that we trade trigonometric arithmetic for exponential arithmetic. Which is much simpler. So for example, if you add two angles, then as you know, the sine of the sum is some expression involving sines and cosines. And similarly, the cosine of the sum of the angles is equal to something involving cosine of one, cosine of the other, minus plus sine of one and sine of the other, right? However, if you're working with exponential functions, then if you want to sum angles, you just multiplying the exponential functions, subtract angles, you're just dividing the exponential functions and so on. So it just makes the arithmetic much simpler. So let's think about this in particular cases of the RLC circuits. So let's consider an RC circuit, right? So assume L is equal to 0 with imposed voltage V of t equals V naught cosine omega t, right? Just like as we were considering a moment ago. So here the equation, since there's no L term, it's just Ri prime plus 1 over Ci equals dv dt, right? Which would be minus omega sine V naught sine omega t, right? Which we complexify to R I tilde prime plus 1 over C I tilde equals I omega V naught e to the I omega t. Okay, so we know how to solve equations like this, linear ODE with constant coefficients. We need to find a particular solution. right? And so if we had started with this equation, then to find a particular solution, we would need to try sine of omega t times some coefficient plus cosine omega t times some coefficient. In this case, because we've switched to having the right-hand side just be an exponential function, our educated guess is I tilde sub p for particular of t is I naught times e to the I omega t. And if we plug this in, so r I tilde p prime plus 1 over c I tilde p, this would give us I times omega times r plus 1 over c times I naught e to the I omega t. And we want that to equal I omega v naught e to the I omega t, right? So we see that that happens precisely when our constant I naught is equal to I omega v naught divided by I omega r plus 1 over c, right? Which we can rewrite by incorporating the I omega into the denominator. We can rewrite this as v naught divided by r minus I over omega times c. Okay, this looks like Ohm's law, especially if we rewrite this as v naught equals this complex constant times I naught, right? So notice this says that the complex voltage is equal to some complex number times the complex current. So it looks like Ohm's law, but with a complex number where we normally have the resistance. So we have a complex resistance, which then gets its own name, the impedance. Okay, so note that, so here r, omega, and c are constants, which we're going to assume are positive numbers. And so the impedance is in the fourth quadrant. Right? If you think of complex numbers, so identify them with R2, right? With the x-axis being the real part and the y-axis being the imaginary part, then a complex number like this, where the real part is positive and the imaginary part is negative, right, lies in the fourth quadrant, down here somewhere. And so that means that if we look at v naught e to the I omega t, that would be equal to this complex number times I naught times e to the I omega t. So as t increases, angular argument of the voltage will always lag behind the angular argument of current, right? So again, if you think of the voltage and the current as being complex numbers, and you think of the complex numbers being in identify complex numbers with R2, so you can think about the polar coordinates of a complex number, right? So you'll have some radius and you'll have an angle, right? And so now we're just looking at the angle, and the angle of this number is obtained by combining the angle of this number and the angle of this number, right? Adding them together. However, the angle of this number, because it's in the fourth quadrant, right, is a negative angle between 0 and pi over 2. And so the angle of this one is always going to be behind the angle of this one, right? So in this situation, we say that the current leads the voltage. Okay, so now suppose we did the same thing, but starting with an LR circuit, right? So the situation where C is equal to 0. Well, let's say instead C is absent. Right, so you just don't have a capacitor. Of course, since you're dividing by C, you don't want C to just be 0. So in this case, if you have an LR circuit and we skip ahead to the complexified equation, it would look like L times I tilde double prime plus R times I tilde prime equals I V naught I omega V naught times e to the I omega t, right? And so you would guess as your particular solution I naught times e to the I omega t. So this leads to V naught equals R plus I omega L times I naught. And then since the complex number R plus I omega L is in the first quadrant, here the voltage leads the current. In a full RLC circuit, we get V naught is equal to R plus I times omega L minus 1 over omega C times I naught. And so here, the impedance R plus I times omega L minus 1 over omega C can be in either the first or fourth quadrant. So for the general case, we don't know a priori whether the voltage will lead the current or the current will lead the voltage. Instead, it depends on the relative values of omega, L, and C. Okay, so we'll stop there. Feel free to stop listening. I'll now talk a little bit about historical context, which will, of course, not be on homework or exam. This time, I thought I'd tell you a bit about Mary Somerville, because this fits in nicely with our discussion of Laplace from last time. So Mary Somerville, Fairfax, who lived from 1780 to 1872. Right, so for context, Laplace lived from 1749 to 1827. So Mary Somerville is a really good example of one of the many women who overcame a dearth of opportunity and the explicit misogyny of her society to contribute to our scientific knowledge. Somerville was born in Scotland, where she received next to no education. Her mother taught her to read, but didn't consider it necessary to teach her to write. Her parents were only interested in educating her in pursuits considered ladylike, such as needlework, piano playing, and painting. One day she overheard her painting instructor, when he was explaining to another pupil, a boy, that Euclid's elements form the basis for understanding perspective in painting and also the basis for understanding astronomy and other sciences. Having overheard this, she then went and acquired a copy of the book and started studying it on her own. Her parents actively discouraged her studies, claiming that the strain of abstract thought would be too much for her. Despite this, she taught herself Latin and she taught herself Greek, and she would get up early, play the piano, and paint during the day, and then stay up late studying Euclid and algebra. Her first husband, Samuel Gregg, whom she married in 1804 when she was 24, had no interest in science and did not understand why she would want to learn any. He died 3 years after the marriage, and it was only then, when she became a widow with 3 small children, that she began to do novel mathematics. It was at this point that she read Newton's Principia and Laplace's great book on celestial mechanics entitled Mécanique Céleste, and other important mathematical texts. At the encouragement of a friend of hers, who was a professor at the University of Edinburgh, she started to solve mathematical problems that were posed in the math journal of the military college. And she was awarded a silver medal for her solutions in 1811. She married again in 1812. Her second husband, Dr. William Somerville, who was a hospital inspector, supported and greatly aided her studies. They moved to London in 1819, and while she was there, she tutored Ada Lovelace, daughter of Lord Byron and the world's first computer programmer. Together, they attended scientific gatherings where they met Charles Babbage. In fact, I found one place that claimed that Somerville was the person who introduced Ada Lovelace to Charles Babbage. At this time, Somerville and her husband moved in the leading scientific circles, and she got to know prominent scientists in England and also later in Paris. They took a trip there. She published some work on magnetism and the solar spectrum in 1826. In 1827, Somerville was commissioned by the Society for the Diffusion of Useful Knowledge to translate Laplace's Mécanique Céleste into English. She went far beyond a translation. She explained in detail the mathematics involved. So this was no mean feat, because we know that Laplace used the phrase "it's easy to see" many, many times in this book. And Laplace's assistant, Jean-Baptiste Biot, later acknowledged that what would happen was Laplace was frequently unable to recover the details in the chain of reasoning in his work. And if he was convinced that the result was correct, then even though he couldn't figure out how to obtain the result, he would just say, oh, this is easy to see, state the result, and then keep going. Somerville's translation, which he entitled The Mechanism of the Heavens, added full explanations and many really useful diagrams that made the text comprehensible. Her book was eventually used as a textbook for advanced courses at Cambridge University for decades afterwards. The book was extremely well received, both by the general public and the scientific establishment. Her next book, The Connection of the Physical Sciences, was an ambitious summary of astronomy, physics, geography, and meteorology, right, study of weather, where she aimed to show the essential unity of terrestrial and astronomical science. This book was also very successful, and it went through 9 editions. In the 3rd edition, in 1836, she wrote that the difficulties in calculating the position of the planet Uranus may point to the existence of an undiscovered planet. So this hint really inspired the British astronomer John Couch Adams to look for and discover the planet Neptune. Somerville's book also was cited by James Clerk Maxwell as one of his formative influences. Really interesting little factoid is that in the review of this book by the Cambridge Don William Whewell, he invented the word scientist. Before that, people were referred to either as natural philosophers or a man of science. But Whewell wanted to use a different word. He came up with the word scientist, and analogous to the word artist. And he wanted this not just because it was a gender-neutral term, but because he wanted a word that actively celebrated the ability to synthesize separate fields into a single discipline. Somerville received many honors after writing this book, including a public pension from the British government and membership in the Royal Astronomical Society, making her the first female member. Another of her books, Physical Geography, right, this is as opposed to, say, political geography, was the first textbook on this subject in English and was her most popular work. It was used as a textbook well into the 20th century. Such was her prestige after writing these books that when John Stuart Mill, the British philosopher and economist, organized a massive petition to Parliament to give women the right to vote, he had Mary Somerville put her signature first on the petition, right, to give the petition more weight. Somerville died in 1872, and in 1879, Oxford University named one of its colleges after her. When she died, one of the prominent London newspapers declared in her obituary that, quote, whatever difficulty we might experience in the middle of the 19th century in choosing a king of science, there could be no question whatever as to the queen of science, end quote. Okay, we'll stop there. Talk to you again next time.